Today we're going to work on proving identities. So when we prove an identity, our goal is to show that one side is equal to the other side. So in this first example that I have on the page here, it says that these two sides are equal, but we want to prove it. So we're going to pick one side and use the fundamental identities and algebra to rewrite the expression until we simplify it into this other side. So it's kind of like what we did in the last section, but now we know what we want to get, okay? So it's actually a little easier than the last section because we didn't really know where we wanted to end up, right? If we just have this and it says to simplify, well, why can't I just leave it like that? But now I know I want to show that it's equal to the cosecant of alpha. So when we do this, it's really important that you do not treat this like an equation where you're working both sides of the equation. So you're not going to do the same thing to both sides. That is not considered a proof. And if you do that, you're not going to get much credit, okay? So what you want to do is pick just one side, and I would recommend just taking, let me start over. Some people kind of just work, this side and then keep writing equals cosecant alpha on the other side. What I usually do is take just the side I want to work and leave the other side out of it, because then you're less tempted to do the same thing to both sides, because that's really hard, especially for students, to stop themselves from doing that. You want to do the same thing to both sides. Okay, so that's really important. And I have some tips here to things to look for, because it's easy to get stuck on these, especially when you're first starting out. The more you practice, the more you'll get the hang of this. So my first tip here is to choose a side that looks like there's more to do. And on part A, or example A here, this side obviously has more involved than just cosecant alpha. With that, all I would think about was, well, that's 1 over sine alpha. I'm still not seeing that those two sides are equal. So I'm going to start with this side. And then I'm going to try to transform that into cosecant alpha. So I'm just going to leave that part up there. Okay, so once you've chosen which side, then you look for ways to rewrite this using fundamental identities, using algebra. You could, if there's more than one term in the numerator, you can split it up into two fractions. If there's more than one fraction, this one doesn't have more than one fraction, but if there is, you can find common denominators and add them up. You can use factoring. You can use the fundamental identities. And if this tip right here we use a lot. We're going to use that on this one actually. If you have secant, cosecant, tangent, or cotangent, you can rewrite those in terms of sines and cosines, and then that usually produces more things to work on. And of course, you want to be familiar with the fundamental identities. If you're not, that will make things a challenge. And then this third bullet here, if you ever get stuck on one side, it's okay to stop and then try the other side. And when you're doing that, if you end up getting the same thing in both of, at one, you work this side, you get to a point, you work the other side, and then all of a sudden you get the same expression where you stopped here, then you've actually proven the identity, and that would be by using method 2. And I think we have well, I'll kind of show you that as we work, as we work through some of the examples. Okay, it'd be better if I have some actual things to point to instead of just a blank page right now. All right, so let's go ahead and start the first example. Like I said, on this one, because we have secant and tangent, there's really not a lot to do here in terms of splitting it up into two different fractions or adding two fractions. I'm going to write in terms of sines and cosines. And when I do this, it's going to create a complex fraction. Recall a complex fraction is a fraction that has fractions in either the numerator or denominator, or both. In this case, it'll be both. So we get 1 plus 1 over cosine alpha over sine alpha plus sine alpha over cosine alpha. And once you create a complex fraction, you know, one thing you can do is use algebra to sorry, I have something in my eye that's bothering me. You can use algebra, or algebraic techniques, I should say, right? This isn't really an algebraic expression, but use algebraic techniques to eliminate the complex fraction. So you have 1, 2, 3, 4 expressions within this bigger fraction, if you will. What's the lowest common denominator of those 4 expressions? Well, it would be cosine alpha. So we can take this fraction times a fraction that equals 1, and we're going to just use the LCD over the LCD. So this fraction is a unit fraction, this equals 1, and that means we're not changing the value of the original expression. So we're going to distribute that through the numerator and the denominator. So cosine alpha times 1 is cosine alpha. Whoops. And then plus 1 over cosine alpha times cosine alpha is 1. Right, so make sure you're distributing, taking it times all terms. It doesn't just cancel here and you get 1 plus 1 equals 2. That would be incorrect. You're distributing. Then we get sine alpha, cosine alpha, plus here the cosine alphas cancel and we get sine alpha. Now, if you notice in the denominator, these both have sine alpha in the 2 terms here. We could factor that out, and that's helpful because once we factor that out, we're left with the other factor, cosine alpha plus 1, which happens to be the same expression in the numerator. So these will cancel, right? Think of this as one factor, and the other factor, of course, is 1. And we're left with just 1 over sine alpha, which is equal to the cosecant of alpha. That's what we wanted to get, so we've just completed the proof. So you started with the left-hand side. Sometimes I abbreviate and write left-hand side, right? And then I've shown that it equals the right-hand side. If you don't want to write this down, I would be okay with you just writing LHS for left-hand side equals, and then you could skip to starting to write what that equals. Right, so once I've shown the left-hand side equals the right-hand side, I'm done. We've completed the proof. So notice some things. 1, I didn't work both sides, of course. 2, when I wrote down my expressions, they all have my variable in them. Make sure you do that. 3, this step right here, I don't want to just see you write, and I talked about this in the last section, don't just write cosine alpha and then it shows up in the top and the bottom. You have to write the unit fraction. Every step needs to be equal to the previous one. Show your equal signs. And use them correctly. You're writing a proof, you need to be complete. No skipping steps. You want to write it so that somebody else can read it. So you don't want to, just go from, even if you see it, you can do it in your head, because I could do it in my head, right, because I have lots of practice. I'm still going to show this step because I want somebody else who comes along to be able to see what I did. So I'm not going to just go from here to here. I'm going to put that step in there so it makes sense to somebody else. Okay, so no skipping steps. Using equal signs and using them correctly so each step is equal to the one before. Alright, let's do another. Okay, in B, on the right side we only have cosine theta, so obviously not a lot we could do there. So let's pick B, So we got 1 plus theta over secant theta minus cotangent theta. Okay. So there I see a couple ways we could go here. One, we could write in terms of sines and cosines. And then another is, because we have two terms here, we could just go ahead and find a common denominator. Let's get a common denominator first before we do sines and cosines. So, because if we, it's going to work both ways, I think, but if you do sines and cosines, then you get this complex fraction that you need to simplify before you combine the two terms. So let's combine them first. All right, so the common denominator between these two would be secant theta. So I'm going to leave this one. It already has that denominator. Oh, I just saw another way to do this too. There's always more than one way to get to the answer. So cotangent, actually the way I just chose here might be the longer way. Now that I'm looking at this again. Okay, I'll show you the other way too. All right, so then, oops, sorry, what am I doing here? Secant theta in the numerator too, right? So this is equal to cotangent theta. So then we have 1 plus cosecant theta minus cotangent theta secant theta over secant theta. All right, so let's write in terms of sines and cosines now. So this is equal to 1 plus 1 over sine theta minus cosine theta over sine theta times 1 over cosine theta over secant theta. Oh, well, I left that because I'm seeing this up here, what's going to happen here. These will cancel, and 1 over sine theta, I'm just going to leave that. So I got 1 plus 1 over sine theta minus 1 over sine theta, which will just add up to 0. I definitely took the roundabout way here. But that's the way it goes sometimes with these. So these cancel, and I've got 1 over secant theta, which is cosine theta. Okay, and that's what I wanted to get, so I'm done. But like I said, there's a couple other ways to approach this. The one I saw after I started was to take this fraction. So here's another way. I think this will go faster. So I'm just going to use left-hand side, equals. Take this fraction and split it into 2, so you get 1 over secant theta plus cosecant theta over secant theta minus cotangent theta. And then 1 over secant theta is cosine theta. And then cosecant theta is 1 over sine theta. Secant theta is 1 over cosine theta. And I'm just going to leave that one for now. This actually then becomes cosine theta over sine theta. And you divide by this fraction, you multiply by the reciprocal, so the cosine ends up on the numerator. I would write that out some more, but I'm running out of room. But you can do that, right? Take this and write it as 1 over sine theta times cosine theta over 1. You'll get cosine theta over sine theta. And notice this is cotangent theta. So notice I put this step in here even though, I can see that these are going to cancel. I still put it in. These add up to 0. and I get cosine theta, which is the right-hand side. So there's another way you could have done it. And I think another way would be you could have wrote just this fraction in terms of sines and cosines, simplify the complex fraction, and it will all reduce out again to cosine theta. So we don't always do everything, you know, take the same path. That's okay. There's more than one way to do these. Okay, I'm going to take a little break here, and then we'll do, let's see, how many more do we have? 3 more to do.